So we're ready to move on, and as you may know, there are three major boundaries in hardware. This is CPU, this is I/O, and this is memory. And our next speaker will focus on the memory one. So please welcome Ivica Bogosavljević. The stage is yours.
So I need the remote. Hello, welcome. Today we talk about memory operations and memory optimizations. I'm Ivica Bogosavljević. I work as a performance engineer, and I focused mostly on small companies that need a performance engineer, but they don't need it full time, so I work as a freelancer performance engineer. So let's talk about memory performance. Now, you know that in the modern software, memory performance is one of the biggest problems because memory throughput is memory is simply much slower than the CPU, and this creates a constant problems. We call software that is limited by the amount of data it can get from the memory subsystem. We call that software memory bound, and essentially in memory bound software there are two types of bottlenecks. The first bottleneck is throughput bottleneck. So let's say you have L1 or L2 data caches and their maximum throughput, let's say 40 gigabytes per second or 100 gigabytes per second. This is the throughput bottleneck. And the second bottleneck is called the latency bottleneck. This is the bottleneck that you get from the moment that you issue a request to the memory subsystem until the moment this request is actually executed. And you will see later that some software tends to be more throughput bound, and some software tends to be more latency bound. And we will show techniques that you can use to mitigate problems for throughput bound software and also for latency bound software. So a short introduction about the memory subsystem. The memory subsystem consists of memory, which is outside of the CPU, and data caches. Data caches are smaller than the memory, and they hold parts of the data that is accessed most frequently. If a piece of data is in the data cache, its access to it will be fast. If the piece of data is not in the data cache, access to it will be slower because the piece of data needs to be fetched from the main memory. Many programs nowadays, especially those that are written using object-oriented paradigm, which has a lot of abstraction and so on, use memory inefficiently. And for us, the programmers who know how the memory works and we know how the system works, we can take advantage of this knowledge and write programs that use memory more efficiently, and therefore they're faster. In this talk, I'm going to talk about these techniques, how you can figure out first if your program is memory bound, and in the next step how we can optimize and make it faster. Now, this is a really important thing for high performance, high throughput systems, and this conference is all about how to achieve higher throughput and higher bandwidth. So what decreases memory efficiency? What constructs in your program decrease memory efficiency? So everything that has to do with pointers in one way or another is potentially can lead to data cache misses and fetching memory that is not in the data caches. Not necessarily, but most of them can do. So imagine you have a class, and in class you have a pointer to some object. If you access that data through that pointer, if you dereference a pointer, that is potentially a data cache miss. If you have heap allocated objects, again, dereferencing a pointer is potential data cache miss. If you have vectors of pointers, this typically happens with polymorphism. If you have polymorphic objects, you need to have objects of pointers, and then these dereferencing pointers, because pointers can be scattered, so that the objects can be scattered in memory, and this is completely irregular access to memory. This can lead to data cache misses. If you have code that chases pointers, so pointer chasing happens in linked list. You process a data, and then you dereference the next pointer, and dereference the next pointer. There is a chain of pointers. And if you have that kind of code, this can also lead to decreases memory efficiency. If you are iterating a linked list, if you're iterating a binary tree, that also. So everything that has to do with pointers often includes decreases memory efficiency. Next is if you have an array, so it's a continuous block of memory, but you're accessing data in that array in a random fashion. So you're not going through the array from 0 to n or from n to 0, you're just jumping random of the array. And this happens, for example, with these data getters and scatters here, when you have histogram of A of I, and this A of I holds some random values. Happens with hash maps. If you remember how hash maps are implemented, this is a big block of memory, but you're just randomly calculating hash and use it as an entry to that hash map. So this is also random memory accesses. If you have working with heaps, like heap sort, this is also memory inefficient algorithm. Actually, the reason why heap sort is 5 times slower than quick sort is because it's less memory efficient. Quick sort just sweeps through array from left to right many times. If you have trees stored in array, so if you have, remember the way you can store trees using pointers, but you can store tree in an array if this is position n is the current node, 2 times n plus 1 is the left, 2 times n plus 2 is the right child in the array. Now, this was what decreases the efficiency of the memory subsystem. What increases memory efficiency? So if you have a data stored in a vector or an array, and you're iterating through it sequentially, you're going from left to right or from right to left, that is generally memory efficient. If you have small classes, so imagine you have big class versus you have a small class stored in an array, access to smaller classes is generally more efficient. Now, if you're doing some software processing, you want peak performance on your hardware, generally you will need to store your data in arrays or vectors, block of continuous memory, and you will need to access them sequentially. Next, what increases memory efficiency is you have small working sets. So imagine a binary tree which is 8 kilobytes, which can completely fit the level 1 cache, versus another which is 8 megabytes, which doesn't fit L1, maybe it fits L3, maybe not. But access to the small binary tree is much, much faster than to a large binary tree. Next thing is what is accessed together should be close neighbors in memory. So imagine you have a class and you're declaring members. Those members that you access together, you should declare them one after another. The compiler will then put them next to one another in memory. Also for linked lists. So imagine you have linked list and there is a logical ordering of elements. So ordering node 0, node 1, node 2, node 3. They can be scattered anywhere in memory. But if you put node 0, node 1, 1 through physically one after another in memory, this access will be faster. Same applies for the binary trees. Okay. So the next question is, what parts of the memory subsystem, how do they influence performance? So I said we have main memory, we have data caches, we have smaller level 1 data cache, which is really small, about 16 kilobytes, 32 kilobytes, level 2, which is 256 kilobytes, maybe 1 megabyte, and level 3, which is 6 megabytes, 20 megabytes. Now, the smaller data caches are faster, so we want to have small workloads. The data cache size actually determines the performance of some operations. Next is the eviction policy. So what is eviction? Evictions is you have a piece of data in your data cache, but you don't need it. So some new data is coming to the data cache. You want to get rid of some data from the data cache to make place for the new data. You need to rid of some old data. And you want to normally the cache will remove the data that is least recently used. It was least recently used and it figures we won't be using it, it will remove it from the data cache. Now, the idea for us is to reuse the data before it leaves the data cache. The next thing is cache line size. Now, caches, data is brought from the memory to the data caches in blocks of typically 64 bytes. It can be more or less, but most of the modern CPUs have 64 bytes. Now, you get 64 bytes of data from the memory to the data cache. Now, you should consume all of it. You should not leave anything unconsumed. Now, imagine you have a linked list node, 24 bytes. You get one node, 24 bytes, but with it comes additional data. So it's 64 minus 24. So you get additional 40 bytes of data that was brought from the memory to the data cache, but it was never used. And you want to use it all. With regards to cache line size, cache line utilization, sequential access are the best. With sequential access, you're always using all the data that is brought from the memory to the data cache. When you have jumps, or you have random memory accesses, that is not the case necessarily. You can make it, but not the case. And finally, the one mechanism is called prefetching. So with prefetching, CPU prefetches data from the memory. So there is a hardware part in the CPU. It's a piece of hardware. It detects the memory addresses that the CPU is accessing. And then it figures out the pattern. Let's say we are accessing memory address 0, 16, 32, 48, 64. And it figures out this, and it starts fetching data from the memory to the caches before the instructions are even issued. So the data is ready there. Now, programs with predictable memory patterns, with sequential or strided, sequential is just going one after another, strided is with jump, but it's fixed length, the stride. These are generally faster than just randomly jumping around memory. Okay, so how do we improve memory system efficiency? So first is we want to avoid unnecessary memory access. Once we get data from the memory to the CPU registers, we want to use them as much as possible. We want to move them away and never touch them again. That's the ideal scenario. So imagine you have two loops. Let's say one loop calculates minimum, and the other loop calculates maximum. They're running over the same data set. So data is loaded, calculated minimum, then loaded again, calculated maximum. Now, if we merge these two loops into one loop, it's called loop fusion or loop jamming. We get performance improvement. We iterate over the data set only once. And C++ ranges actually is a loop fusion just brought to another level. So I have an experiment here. So I had a vector, class size 16 bytes, 100 million elements in the vector. And when I had a loop fused minimum and maximum, it took 270 milliseconds. But when they were in separate loops, it took 368 milliseconds. Okay, so this is the way just you remove, instead of accessing 100 megabytes of data, you access 50 megabytes of data. Okay, the next technique is changing the data access pattern. So changing the data access patterns means the data doesn't change in memory. The layout remains the same, but the difference is that you're accessing the data in a different manner. There are a few techniques that change the access pattern. One is loop interchange, loop tiling, and loop sectioning. So I'll go through them here. Loop interchange. So what happens here? This is a classic matrix multiplication code. So we have here that it goes 3 nested loops, and the innermost loop calculates something. Now what happens, we need to analyze the memory access pattern for access to C, to A, to matrices C, A, and B. Okay. So the innermost loop iterates over K. So when K increases by 1, what happens to C, to A, and to B? When K increases by 1, so the matrices are stored row-wise. So each row is one row after another row. So when the K increases by 1, A, it just moves to another sequential. It's a sequential access. It moves to next neighboring element in memory. With regards to C, when K increases by 1, it doesn't. It's always hitting the same address in memory. So actually, the compiler would remove access to CI of J and move it to a register access. It wouldn't go through memory. And finally, the access to B of KJ. So if you see B of KJ, when K increases by 1, we are accessing the next column. So we have this jump, which is the row size. We are jumping row size, and this is memory inefficient. Now, can this be fixed? Yes, and the way to do it is through loop interchange. So on the right side, you see looped interchange. What happened is that we took the loop over J and made it the innermost loop. Now let's do the analysis again. The analysis A of IK, the J doesn't figure. So this is A of IK is a constant access. You're hitting the same memory address again. The address of B When j increases by 1, it's a sequential access, so it just increases by 1. And what happens with C? Well, with C happens again the same as with B. It becomes a sequential access. So we don't have this access with the jumps. We have only sequential accesses, and actually this is much more efficient. When I measure this matrix size 1,200 times 1,200, original code took 5.8 seconds, and the second version took 1.22 seconds. The next is loop tiling. So let me explain what loop tiling is. So here you see we have an example on the left side. These are two matrices, again, that we are accessing. The matrix A of ij is accessed row-wise. So we go row by row. And this is sequential access. We are just accessing sequentially data. But the matrix B of ji is column-wise. We are going columns. Because the matrix is stored row-wise in memory. So we are jumping. From the perspective of hardware, we are jumping over rows. Now the question is, can we fix that with loop interchange? We can't, because it will just access to B will be efficient, but access to A will be inefficient. So we do it like this. So from the original on the left, we move to the tiled or blocked access on the right. We divide the matrix into small these tiles, and then we access them small. We access them like that. And this is actually more efficient. Now the question is, why is it more efficient? So what happens is that with the column access, what is the problem with the column access? When you access row 0, so column 0, row 1, row 2, row 3, you get the row 0, but you also get, because the cache lines, the data is brought from the cache line, you get free access to column 1, column 2, and column 3, row 0. You get access to column 0, you get row 0, column 0, but you get free access to column 1, column 2, and column 3. Now you iterate over the end of the columns, and if the number of columns is large, the first access will get evicted because it's too far away. It's too far away. Now when we change it to the right side, when we change the access pattern, what happens is that it's similar to the matrix becoming smaller. The matrix is smaller. It's let's say it has 16 rows, and you're accessing 16 rows in column 0, then moving to 16 rows in column 1. This data is already present in cache. It's not evicted. And in this way, we get performance improvement. So when they measure this, so I didn't do this experiment. When they measured it, it went from 2.69 to 0.45 seconds. Okay. So I explained why loop tiling is faster. Moving on. So originally this was a quiz, but we don't have time. So let's say you have n image processing algorithms. You have image processing algorithm 1, then image processing algorithm 2, and image processing algorithm 3, and so on. It's a pipeline of algorithms. Now what happens is your algorithm loads the image 0. So in this pipeline, the output of algorithm 0 is the input of algorithm 1. The output of algorithm 1 is the input of algorithm 2. So it's simple. The question is, this is memory inefficient. And the reason why it's memory inefficient is each algorithm loads the image, does the processing, stores the results, and the meantime, since the result is large, the results gets evicted from the data cache. Now the second algorithm, the next algorithm, loads the same data from the memory to the data caches, does some processing, returns it back, and so on. So you have data going from the memory to the CPU, from the CPU to the memory. Data caches are mostly are not used for anything here. So how is this solved? So the technique is called kernel fusion. So you have this algorithm. Instead of working on the whole image, you can work on let's say one row. You work on one row of the image, then move to the next algorithm, one row of the image, move to the next algorithm, one row of the image. Since one row is much smaller, since one row is much smaller than the whole image, it will remain in the data cache. And when it remains in the data cache, that means the access to it will be much more efficient. If you measure the amount of megabytes transfer from the memory to the memory, this will be much lower. There is one language called Halid, which is actually You can program in that language, this is for tensor, for image processing. You can just simply describe operations and it will generate code that is memory efficient. So, okay, next thing is, until this point, we didn't change the data, how the data is stored in the memory. But from now on, we need to change how the data is stored. We need to change the data layout and memory layout. Data layout is how compilers store stuff in memory. The compiler determines data layout. And memory layout is determined by the system allocator. So how malloc and free returns chunks of memory. What are the techniques? If we have large classes, we should make them smaller. If we have classes that have some unused members. So we have our hot loop, which is important. We want to optimize it for speed. It accesses data members in some classes, but it doesn't access some other data members. If we remove those data members, we will make it faster. We want to move in data from other classes. So we want to keep all of our data that we're processing in one place. We don't want it scattered around memory and moving it and this way and that way and so on. We want to avoid that. And finally, there is this technique called structure of arrays. I'm going to explain it a bit later. So this experiment with class size and memory layout, the algorithm is nothing fancy. I'm just going to show you the numbers. So originally, on the x-axis, you see the size of class in bytes, growing from 20 bytes to 504 bytes. On the left side, you see the runtime. And you'll see there are two different algorithms, the red algorithm and the blue algorithm. And you will see that as the class size grows, the performance gets worse. And after some time, it gets really, really bad. So you want to keep your classes small. And actually, I don't know how many of you have heard about data-oriented design. But data-oriented design, actually, one of these tenets is to move things, to keep all that is accessed together in one class and then break the big abstraction into smaller classes and store them in separate arrays and then process them separately. So this is one of the big tenets of data-oriented design. So why is processing of smaller classes faster? Well, the answer is actually quite simple. Now you have some hunch, you have some idea what's the problem. The data is brought in the cache line sizes. When you have smaller data, everything you bring from the memory to the data caches you actually consume. When you have large classes, you're bringing data that you're not consuming, you're wasting memory bandwidth. Yes, so next is structure of arrays. So how does that work? When we have classes stored in an array, we can change the data layout. Instead of using a vector that contains instances of a class, let's say we have a vector that each element in the vector is a class. We convert it to, this is called array of structures. We convert it to structure of the array. And each member, so instead of let's explain through an example. So on the left, you have a class student. It has a name and average mark. This is array of structure, that's the original. And we have a vector named students. On the right, you have a class called students. And inside, you have names as one vector and average marks as another vector. Now imagine you want to calculate average mark for all students. Now, the original code took 194 seconds, and with this modification, it took 42 milliseconds. Again, the reason is cache line sizes, cache line utilization. For average mark, we don't need the name. We don't care about the name. We only need the average mark. We only need the number. But with the implementation on the left side, we are bringing both name, some part of the data related to the name, and the average mark. We are wasting memory bandwidth. And actually, this technique is quite powerful. For those that use vectorization to speed up the data, they use this a lot. Okay, so next thing is called changing the data structure layout. So it's very similar to changing the data layout, but not related to classes. So imagine so how do you change the data structure layout? For example, if you have a vector of pointers, and pointers will point to random places in memory, you can use vector of STD variant. It consumes more memory, but these memory accesses are much more efficient. Next thing is, for example, with linked list, you have unrolled linked list. So here on the right side, the image shows the unrolled linked list. In linked list, typically you have one value and then pointer to the next element. With unrolled linked list, you can have more than one values in a single node. So here, see that the first one has 3 values in the single node. The second one has 2 values, and the memory efficiency of such accesses is much better because a single node can fit a single cache line. So you don't have to bring the data from the memory too many times. Also, instead of binary trees, you can use ternary trees, quaternary trees, which are more memory efficient for the same reasons, because cache line utilization is better. And also these trees are much shallower. Actually, the decision to use binary trees in C++ STL was brought in the 90s, and at that time, this problem with the memory efficiency didn't exist in the way that it exists today. Okay. Next thing is, so we talked about changing the data layout. Data layout is determined by the compiler. Next thing is changing the memory layout. So memory layout is determined by the system allocator. malloc free implementations, actually malloc implementation. malloc returns chunks of data, and whether these chunks are neighbors in memory or not neighbors in memory, this is actually, you'll see that it is really important for performance. Memory fragmentation. Memory fragmentation is a problem on long-running embedded systems. So actually what happens is that as the time runs, you run out of memory because you cannot find a block of memory of appropriate size. But that is not the only problem. The problem is also that these accesses are not efficient anymore. Your program is not allocating neighboring, your system allocator is not allocating neighboring elements in memory, neighboring chunks in memory. Instead, you get some random chunks from random reusing, to reuse chunks and decrease the reuse chunks and decrease the memory consumption. And this is not good. So for memory layout, one of the things that you can do, and it's also done often, is use flat data structures. So flat data structures is just, let's say, binary trees where all the data is allocated from one buffer, and it doesn't mix with another buffer. This increases the locality of reference and makes these structures faster. With tree layouts, binary trees have several layouts, and one of them is called 1M de Boas layout. This one is really interesting. I don't have time to cover it in this session. And you can look it up and see how it goes. How do we modify memory layout? We can use with a dedicated memory allocator. Now, there are a few types of memory allocator. One is per instance. Let's say you have a binary tree which is really, really large, 8 megabytes. And it allocates, let's say, 1 million chunks of data. It makes sense for that one particular binary tree to allocate all data from a single block and to have a dedicated allocator just for that memory tree. Next is per type memory allocator. So with, for example, std string. std string, each instance does one call to allocator. So it doesn't make sense to have an allocator per std string. Then you would have allocator that is shared for all std string instances. Also, you can replace the data allocator, the global data allocator, and there are several of them available. tcmalloc from Google, memalloc from Microsoft, jmalloc from Facebook, and they all promise and actually deliver the promise that on memory-intensive programs, you can get like 5% speed improvements with very little effort. Okay, here an example of linked list memory layout. So we have 3 memory layouts here. One is called random memory layout. The second one is compact memory layout, and the third one is perfect memory layout. So random is just that the nodes are in memory stored somehow, without any ordering. Compact is this, that they are stored in one block of memory, so it's really compact. But actually, the access, they're not. There is no physical ordering of them. They're just stored randomly in this compact block of memory. And the third one is a perfect memory layout. With perfect memory layout, you have that logical neighbors in linked lists are also physical neighbors in memory. Now the question is, which one of these layouts are best for iterating? And the answer is, depends. If you have small, medium, or large. If you have small linked list with 128 doubles, it doesn't matter. But you have a large linked list. The random layout takes 15 seconds. compact layout takes 9.7 seconds, and perfect layout takes 0.12 seconds. Now, the perfect layout is 100 times faster, and the reasons, there are several. One is that the prefetcher can actually figure out the memory access pattern and get the data we need earlier. The second is that cache line utilization is much higher with this one. So everything we get from the memory we actually consume. You can control the memory layout of linked list or a binary tree using a custom allocator. Okay. The next bottleneck is called, so all this was throughput bottlenecks or maybe mixed latency throughput bottlenecks, but now we'll talk about latency bottleneck. So what is a latency bottleneck? Throughput bottleneck means I have 100 gigabytes per second. I'm running at 100, maximum theoretical throughput of my memory is 100 gigabytes per second. I'm running at 100 gigabytes per second. I cannot go any faster. That's the throughput bottleneck. Latency bottleneck happens when there is no bandwidth saturation. If you measure it, everything seems fine. Now, question is, what's the problem? The CPU is limited by the memory subsystem latency. So the CPU can issue instructions in advance, but the problem is it doesn't have any instruction to issue, because in order to issue instruction in advance, it needs to get the data for the current instruction to move on to issuing further instructions. So codes that exclusively exhibit this problem in the memory domain are chains of pointers. So linked lists and binary trees, these are chains of pointers. And also hash maps with separate chaining, but that happens only if you have a lot of collisions. So separate chaining means that if there is a collision in a hash map bucket, they will be chained like a linked list. So essentially it's again a linked list. The chain of pointer is a dependency chain for the CPU. It cannot move on to process the next element in the chain until it has finished processing the current one. And this is the latency bottleneck. So how can you fix the dependency chains? How you can fix the problems with dependency chains? There are total four techniques. One is, just a second, so one is interleaving two or more dependency chains, one to make them shorter, one to run through them fewer number of times. So let's say you run 1,000 times. If you run 500 times, it's faster. And the last one is to remove dependency chains altogether. So interleaving dependency chains. Imagine we have n linked lists. We have several linked lists. Now, one way to do it is go to linked list 0, go to linked list 1, go to linked list 2, and so on. If we want to interleave, we can, let's say, process four linked lists in parallel. So we have node 0 of linked list 0, 1, 2, 3, node 1, linked list 0, 1, 2, 3. So this is called interleaving because we are processing. We are giving to the CPU more available instruction level parallelism, and that makes that code faster. With trees, that's an interesting example. Let's say we have n values in the trees that we want to look up, check if they're in the tree or not. We can do them, instead of doing them one by one, we can do it in parallel. And this is how it looks like. So on the left side, you see a tree. It's a tree that if you're, if you're in the node of the tree, the left child is smaller than the current node, and the right child is bigger than the current node. And this is a lookup data. It's 1, 7, 10, 11, 14, 18. Now, how would be a typical lookup look like? So let's say we're looking up 11. You go to 10, it's bigger. 11 is bigger than 10. You go right. You go to 14. 11 is smaller than 14. Go left. You go to 12. 12 is bigger than 11, you go left, it's a null pointer, so this is not available. Now, parallel lookups do a bit different. So, let's say we have a current node for 1, 7, 10, 11, 14, 18, and so on. So in iteration, the current node for all is 10. It's the root node. And actually, for this, 10 is found. We don't need to move on. In the iteration 2, we now have current node, which is for 1 is 7, 5, and 5. 10 is found. For 11 is 14. So we move into a second level of the tree. And for 18, it's 14. In iteration 3, we have again, we are on the third level of the tree, and we have found or not found. So we are going through this array 3 times. So we go through this array, the depth of the tree. But actually, this makes these lookups faster. So in my experiments with binary tree size and runtime, you see that the simple runtime, they're mostly the same when the tree is small, but as the tree size grows, interleaved becomes much faster than the simple runtime, because the CPU has more work to do, available instructions to execute. Okay, so shortening data dependency chains. Shortening is actually can be do the same way as explained earlier, unroll linked list. So with unroll linked list, let's say you have a simple linked list that calls 1 element per node. It has 1,000, the length of the dependency chain is 1,000. But if you unroll it by a factor of 2, the length of that linked list, actually the length of the dependency chain is 500. With trees, if you use n-ary trees, ternary, quaternary instead of binary, you give the CPU more things to do. Next things you can do, decrease number of passes. So dependency chains remains as it is, but instead of passing through it X times, you pass through it a fewer numbers of time. So how would that work? So let's say like this. You have n values in a vector that you're looking up in a linked list. Now you can invert the lookups. You can, instead of looking up, you take a value from the vector and then you go through a linked list, you invert it. You take a value from a linked list and you're looking up in the vector. And actually, lookups in the vector don't have problems with the dependency chains. They're much faster. This is one way how to solve it. And finally, breaking dependencies. This is more difficult. It requires thought, it requires designs. For linked lists, for example, one of the ways to do this is you have a linked list. On the first pass, you pass through the linked list, you create a copy of a linked list and store it in an array. And all the other passes, instead of going through the linked list, you're going through an array. You're breaking. So you only once pass the linked list, and in all the other passes, you're passing through an array. Also, you can have a linked list again, but you create a copy in an array, but not a copy of data. You have a copy pointers to the nodes in the linked list. When you iterate the linked list like this, you don't have chains of pointers. So this access is also much faster, especially for really large linked lists, because the latency of large access is much bigger. Also, if you have if your current node is X, so you can, instead of using binary trees with pointers, you can convert it to binary trees in arrays. So if you have in an array, if you store a tree, if the current is X, so the index of the current node is X, the index of the left one is 2x times plus 1, and the index of the right child is 2x plus 2. And I actually did experiments on this one, and this is the difference between those two approaches. So pointer-based runtime and array-based runtime for binary trees are mostly the same when the binary trees are small. But as the size of the binary trees grows, then they become, the array-based runtime becomes much faster, and you can see this is almost 2 or 3 times faster. Okay, sorry. And we are almost at the end. So hardware efficiency for us means typically faster software, and memory efficiency, especially for systems that process a lot of data, is really important. Now, memory inefficient problems are typically lookup problems. And compute core CPU limited problems are typically data processing problems. Like convolution is typically CPU bound, but lookup in a binary tree or lookup in a binary search is memory bound. So it is important, when you're doing this optimization, it is really important for you to measure to see if everything is correct, because sometimes the assumptions are wrong. That happens a lot. It's not that uncommon. Okay, this is the end of the talk. Thank you very much. Questions?
Thank you. Thank you very much, Ivica. So, do we have any questions here? I see lots of people. Yeah, here we go.
Hi. You've spent a lot of time discussing the linked lists and binary trees of huge sizes and so on. My question is, why the hell do you ever need them? I mean, I've been in the industry for a while, working on highly loaded projects and blah, blah, blah. And typically, if you need a linked list, in a tight bound loop which processes a lot of objects, you don't really need it.
So I've
If you
seen
need a
for-
huge binary tree,
So
you,
this is like a-
you are probably better with the unrolled structure. The unrolled linked lists are fine, but I'm curious as to maybe there is something I missed. Maybe there is a place where you actually need huge linked lists and binary trees. So I'm really curious about that.
So this is like a slight provocation. So I don't understand like that. So with linked lists is that linked lists are really basic data structures, but you know actually that every person that does some kind of high performance computing avoids linked lists, and that makes sense. But for example, with data filtering, but you're removing data from it, the linked list is a perfect data structure, and I've seen that in production. It's not that uncommon. And secondly is that you have many. Actually, the question of memory performance is how can I take my linked list and use it in some kind of array-based back store and achieve what I want with more instruction level parallelism and more with less data cache misses. That's the essential. You have like in STL, it's called the Hive. It's a new data structure which is unsorted storage that you can add and remove, which can be implemented through linked lists, but actually it's implemented through some blocks of memory that are chained together.
Right, but that's the method to fix the issue. Why would you use a linked list for 1 million objects in the first place? What kind of objects would that be?
Sorry, I cannot answer that question.
Andrei, let's meet in the hall later. So please, next question. Gentleman over here.
Thank you for the presentation. The question is about, for example, loop tiling. Is there any abstractions to help with loop tiling, or maybe some other abstractions to help with data access locality?
Sorry, can you repeat the question?
Loop tiling. Is there any C++ abstraction that can help with that?
No, not that I know of.
Maybe could you provide examples of other C++ abstractions that could help some problems with data access, locality data access?
So, for example, with matrix multiplication, you will use loop tilings. Loop interchange and loop tiling are used together. With image processing, actually, the thing that when I talked about this image processing pipeline, and instead of processing whole image, we were processing just one line. It reminds kind of loop tiling because we're just using smaller parts of the things. The C++ doesn't have any constructs to help you with loop tiling. And actually, if you look at the code with loop tiling, it's really ugly. But that is actually coded. This is the thing that we can actually find.
Thank you.
Any more questions? Please, could you give the mic person over here?
Hi, thank you for the performance in here. So I have a question regarding the CPU. So if, let's say, we've implemented the code that is memory efficient, and we implemented most of the techniques that you've told us about, and at some point we've changed our CPU. Have you faced any problems with that, maybe in rewriting some code to be more optimal for the specific CPU?
No. So normally these memory optimizations, most of them are not specific to any CPUs. All CPUs have these problems. All CPUs except for microcontrollers have data caches, and all these techniques in one or the other sense help the memory efficiency. There are some things with in-order CPUs like ARM Cortex A53, which have some additional problems, but I didn't have time to discuss it now. If you were writing for such code for such problems, the compiler would probably emit instructions so to hide the memory latency, or if you were programming assembly or compiler intrinsics, you could do that yourself. But this is really not, you don't see that kind of CPUs in high throughput systems.
We have a question on the right.
Hello on новой презентации. I have a question regarding the targeted and graph databases. Have you got any experience with graph databases and enhancing their performance based on your techniques?
No. Sorry.
Okay, thank you.
Sorry.
Okay, we have a question here.
Thank you for the talk, and you introduced a lot of memory CPU optimization, and it seems your code may be full of this optimization. And any new developer, for example, may join to the team, yeah? And for example, insert a new field between two other fields in the class, and here your code may get 2 times slower, for example. So how to protect your code from the changes in the future, yes, that may spoil the performance significantly?
No, there is no.
Maybe some recommendation. Yeah, well, no
You
recommendations.
write comments. You write comments. Have good code reviews. There is no like automatic. If you have a testing that's also measures performance and performance degradations, you can catch that in testing. That's also one way. But essentially, sometimes when you see a code, I've seen codes that sometimes you look at the code, you don't know why it's written like that, but there was something in mind. It wasn't commented, and now it's legacy that nobody understands. This happens a lot with performance.
That's enough? Yeah, thank you. So probably 2 more questions. Gentleman near the pillar over here.
Thank you. My question is about algorithm optimizations. Which of them can be done by modern compilers, so I don't need to think about them? Or I need to implement it by myself, all of them?
So, okay, data layout and memory layout, compilers don't do that. So memory layout optimizations are not done by the compiler. You can use general purpose allocator to achieve that. Data layout optimizations are not done at all by the compiler. You need to do them manually. Data access optimization like loop interchange, loop tiling can be in principle done by the compiler, except that in my professional experience, I only seen once loop interchange done by Intel's compiler, which is deprecated now. I never seen GCC or Clang do it. And so at the end, it turns out that you have to do it manually to make sure that it actually happens.
Thank you.
Yes?
So here, Andrei, you have 2 minutes. No more.
I only in 50 seconds. So what's your favorite one? What's the most amazing memory related optimization that you have personally done that was just, wow?
So loop interchange actually can help a lot, and it's really simple. So we did the optimization of image processing algorithm. It was like a naive implementation, was like, 10 seconds, and after that it was 1 second. It was along the thing of wow. Yes.
We have last question, I believe, here. Yes.
Yeah. Hello. Thank you very much for your presentation. So my question is you have mentioned that you are working as freelance for many companies for optimization, and my question is related when you come to a new company,
yes.
Have you got any tools to find out the parts of code where is bad optimization or patterns, how to do that, or you're doing it searching, going line by line, or how it actually looks like?
Yes, so there are tools. This thing I didn't mention, and actually this is the most important thing for a software engineer, is the tooling. And the good thing, so there are good things and bad things about this. The number 1 tool is Perf. So Perf on Linux systems. I mostly work on Linux systems. Intel has a really good profiler called vTune, and vTune can tell you if your program is memory bound or CPU bound, so you have some idea. This all optimization won't work if your program is not memory bound. It's just waste of time. Don't do them. So it is really important as a first step to understand if your program is memory bound or CPU bound. In the next step, you want to measure, let's say you want to measure the throughput of memory, throughput of L1 cache, throughput of L2 cache, and you can do that. There is one library called Liquid. Liquid is really nice because you can select a chunk of code, let's say, and then you can select a chunk of code, you mark it with these markers, and then you can see how much memory it consumed. And you can measure, let's say, I did a theoretical, it should consume 2 gigabytes, but when I measured, it consumed 8 gigabytes. Then you know that you have a bad cache line utilization, and you should do something about it. So there are tools, and you should use tools. You should not do walk in the dark. because that doesn't make a lot of sense. Although the things that I said, the referencing pointers and so on, this is typically what actually causes that problem. But you should confirm it.
So thank you, everyone. Ivica, it's up to you to decide who's our hero with the best question.
Tooling.
Okay. So thank you very much, Ivica. A round of applause to our speaker. Don't forget to rate the talk.